Good afternoon, everyone, or maybe another part of the day if you're joining from further in another time zone. Today we are here together for a SEFI at Work session related to the International Handbook of Engineering Education Research. This is a series of that we will be organizing that is focusing on the International Handbook of Engineering Education, and this is organized by Esther, who is co-chairing the SEEK Engineering Education Research together with me. So what's the idea behind this series? Because today we have our first session, but in the entire series of sessions, we want to focus on all chapters from the International Handbook of Engineering Education Research, and we want to give the floor to the authors of these chapters, which have this high impact publication, this very nice handbook. And in fact, we are joining the efforts with all the special interest groups because we have asked all special interest groups to select one of the chapters that they particularly like, and then to organize a similar SEFI at Work session for this. What do we hope you will get from this session? We will hope to get you a guided reading from the International Handbook of Engineering Education Research, and by this to get some insider info from these authors directly. So not only what's written in the book, but maybe also something more. Furthermore, like this, you will be able to get to know these well-respected researchers and authors in engineering education research, and you might get the opportunity to connect to them or to connect to other people in the audience who are also very much enthusiastic about engineering education research. So today, this is our first session, and it's a pleasure that we have managed to convince Lauri Malmi to present his chapter, A Selective Review on Computing Education Research, which is in fact chapter 26 of the handbook. But I also want to give you some outlook into the future, because in fact we have already 4 more sessions scheduled where other chapters will be selected. First, we'll have the engineering skills, who will be presenting a chapter on the 16th of January. And then in the end of January and the beginning of February, then the Special Interest Group in Sustainability is doing a big effort with 3 sessions connected to 3 chapters of Engineering Education Research Handbook. So please, if you're interested, already write this down in your agenda, but of course we'll also invite you for them later on. Now, without further hesitation, I want to give the floor to Lauri to present his chapter, A Selective Review of Computing Education Research. I also want to point out that we will be recording this session and the presentation of Lauri, such that this can be shared afterwards on the website of SEFI. So in case you don't like you don't want to make yourself visible with your video, please shut down your video definitely during your presentation. If you have questions that are popping up during the presentation, you can use the Q&A button on the top of this webinar to ask your question. And if it's really urgent, you can, of course, always raise your hand, and then we will give you the floor for a short question. But also, at the end of the session, we will really have an interactive discussion with you, where you'll also be able to take the floor, take to your microphone, and talk to us. So, Lauri, if you are ready, then I'll handing you over the screen.
Oh, thank you. Thank you. So I share my screen. You should be seeing it now, I hope.
Yes.
Yes. So I'm happy to be here and present and even start this whole seminar series, webinar series. So. A little bit of my own background. So I graduated at Helsinki University of Technology already almost 40 years ago, and gained my doctorate there in 1997. And then I've been working as a lecturer or researcher in computer science from late 1980s till 2001, when I was nominated as a professor at Helsinki University of Technology, and later on from 2010 it was merged with 2 other universities to form Aalto University. My main research field has, during the whole time, been computer education research, but I've done a little bit work also publishing in engineering education research venues. I'm leading Learning and Technology Research Group, which, in addition to me, has several lecturers and researchers. And our main topics, what we have been working on, is various software-assisted pedagogies to support program education. And then quite recently, we have a lot of work in learning analytics and large language models supporting program education. And my personal interest during the last few years has been exploring the computer education research community and what kind of research has been carried out. So the contents of my presentation, I will first give a very brief history of computer education and computer education research, then present some of the main publication venues and also the main research areas. Then I will specifically look closer at program education research and tools research, which are somewhat unique, strong areas in computer education research and not so much present in engineering education research in the other topics. And then I close with some observations of current trends in the field. So how everything started. Computer education is naturally much younger than engineering education. So it actually started in 1950s in various computer companies which were building the first computers. And university education has started in the field in late 1950s and mainly in 1960s. And in the beginning, it was just professional training to build computers and do software. But now that universities were building up the computer education, there was a need to define a joint curriculum, and ACM set up several committees over the years, about every 10 years, to build the curriculum definition. So curriculum 1968, 78, 91. And as the computing field has then broadened even wider, then it was necessary to start defining curriculum definitions for various sub-areas in computing. And currently, Curriculum 2020 covers 7 subfields, which you can see here, and we can expect that it will grow as the field grows. In ACM 60 was launched in 1969 to create a forum for computer educators to discuss especially computer science education, curriculum requirements, and how to improve computer education. And soon after that, in 1970, the first conference which was focused on computer education was launched, and it was the ACM 60 Technical Symposium. And about 25 years later, and in Europe, because this ACM 60 was only in the US, then in Europe, a corresponding conference was set up in 1996. And then some 20 years ago, there was a sub-community among the wider computer education community, such sub-community who wanted to carry out research rigorously, and the International Computer Education Research Conference was set up in 2005. In Finland, the Calling Conference was launched actually in 2001, but after a few years it was turned into a research conference. And then during the last 10 years, all main computer education conferences, they have had strong research presence, but there is still work. It's possible to publish also experience reports from new educational innovations and tools. If we look at a little bit closer that which of the conferences are, so 6C, as I mentioned, that's targeted teachers and researchers, and it's a very, very large conference, more than 1,500 participants annually. It's always organized in US and or Canada, mainly in US. In Europe, we have ETICSE conference, Innovation, Technology, and Computer Science Education. And that's also targeted to teachers and researchers. And then there is ISER, this International Computer and Education Research Conference, which is targeted mainly for researchers. And that turns out globally every second year in US or Canada, and then every fourth year either in Europe or in Australasia. ETC in Europe has typically 200 to 300 participants. ISER has about 200 participants. And then we have a number of smaller, significantly smaller conferences. In Australasia, there is a ACE conference. In Finland, we have calling conference, which is actually very, very international. So about 80% of the participants are international. And then there are two conferences where focusing on school level computer education, WIPC and ISEP. But of course, computer education research papers are being published in several other conferences as well, but in such conferences which are not solely focusing on computer education, but also publish papers from many other fields. Like in computing, there is ICSE, there is ACM CHI, Human Factors in Computing Systems, and of course in SEFI conference there have been many papers about computer education, and in ASEE in US engineering education conferences, and in general in engineering education conferences, the computer education papers are being published. So, for example, in many of these IEEE conferences. There are two main focused journals which only publish computer education research papers, and these are ASM Transactions on Computer Education and Computer Science Education. These can be characterized as the top journals in the field. But then many other journals also naturally publish papers here, like IEEE Transactions on Education or Learning Technologies, then Computer Science Education, and so on. But actually, papers are being published in hundreds and in other conferences and journals. I was recently involved in a project where we from Scopus database, we downloaded all papers we found. We found which were dealing computer education, and that was about 30,000 papers. Well, actually, we didn't download them; we just the references. And these were published in something like 1,500 different venues. So it was really widely in very different venues. But if you are interested in following the field, definitely these venues that are mentioned here on my slides, they are the relevant ones. Okay, something about the origins of the research. So computing itself draws from three different traditions. There is a strong mathematical or formal tradition, which draws from mathematics tradition, especially theoretical computer science draws from that, and also machine learning draws heavily from that. Then there is scientific and empirical work. So much computing work includes empirical work where you are building models, you are testing them, you are making hypotheses and empirically evaluating them. And then, of course, naturally, from the very beginning, computing is engineering field. Initially, building computers, and then, of course, building software. That has been very central in the field. When you think about what are the research foci in the early years, so research in 1970s, 1980s focused very much on programming. And it was about understanding programming, especially how experts carry out programming, and then how novices learn programming, and what are the differences there. So there is some seminal work published in 1980s, which is still relevant findings. And then this children's learning programming, like Puppet's Mindstorms was published in 1980, and the logo language was already had been present for many years before that. So that was something which was focusing on exactly children's learning programming. If we now think about that, what are the current fields and as the field has grown so much, so I'm now relying on the Cambridge Handbook of Computing Education Research, which was published in 2019, and which covers very much work in the field. So it's a big volume, about 1,000 pages. So looking at that book, that's a very good source of exploring what's happening in the field. So there are certain themes that are frequently occurring in the field. There is always a lot of work on introductory programming, because that has been very much a challenge in computing education. Then there is work on program paradigms, so that means how programs are being constructed. The main paradigms used are procedural, object-oriented, and functional paradigms, but there are others as well. Then there's work always about assessment methods and plagiarism, because, well, students do plagiarize, and there are not lots of research how to treat that, either prevent that or observe plagiarism. There's work about pedagogical approaches, there's work about equity and diversity, and this has been actually quite popular area in the recent years. But as computing then has extended to other areas, there is during the last 10-20 years, there has been much work on computational thinking and computing in schools, teaching programming in schools, because programming has become a regular part of a school curricula in many countries. Or computing in some way, not necessarily just as programming, but computational thinking. But also recently there has been observation that actually teaching computing for other disciplines like humanities, you need different kinds of approaches, not teaching them in Java programming or Python programming, but something different. So this is a new area. Then other areas are system software and technology. So various kinds of software systems have been very important part of computing education research. So various tools, learning environments, and then tangible computing, for example, in the form of robots, educational robots. And then various the development environments, they typically can collect a lot of information about students working, and that can be used in learning analytics to better understand students' work. Then we have areas, teacher and student knowledge. So how teachers should treat various minorities, they will be aware of the inclusiveness. And then how teachers learn and how professional development after formal education continues. Then learning outside classrooms of informal learning is also a research topic, as well as understanding various ways students' knowledge and their misconceptions, their attitudes, motivations, and dispositions. But these are not all the subfields. So the field is really very large. Now I will be focusing on program education research. So one of the challenges in programming education has over the many years has been the large failure rates in the introductory courses. Very often there's used acronym CS1, so meaning Computer Science 1. And these failure rates can be 30% till 50% in many institutions, and that's a very serious problem. And that's why there has been a lot of work exploring various pedagogical methods and practices, various tools to support students and understand why is it so difficult. And it's not just that some if students pass the course, but they have often fragile learning, so that actually they don't know very well what they have learned. And what is there behind these challenges? One of these things is classifying these kind of learning challenges. That first of all, what programming is and what kinds of problems it can address. So what can you do with programming? What you cannot do with programming. And then always in textual programming languages, there have been problems for students in syntax. They have syntax problems so that they cannot construct language statements in a correct way, or understanding language semantics. Then one essential thing for programming skill is understanding that what happens under the hood, and there's an abstraction called notional machine, that what happens on an abstract level when a program is being executed. Then students need to learn schemas, that how to build various algorithms, how to design programs using certain typical patterns, and there are lots of these schemas that need to be learned. And of course, there are practical tools and processes need to be learned. So designing programs, coding them, testing them, debugging them. So if we simply take just very simple Python program as an example. To be able to construct this program and properly understand, the student needs to understand first of all various concepts, variables, loops, and function calls. And then students need to understand that there is strict syntax in Python that you need to follow, otherwise the program doesn't compile. Then this kind of typical schema on writing a loop which collects information and then sums it together, forms one schema, and that's essential that you understand that schema, how the loop counter is incremented and how you test the end of the loop. And you need to understand that how the loop is being executed, and all this you will also need to be able to code this and compile it, and you need to test and debug it if needed, if there's some error. And everything here you need to have and understand together to be able to successfully construct this small program. So that forms what is called a high element interactivity, that you cannot easily isolate certain things in learning programming and learn those separately, but you need to be able to master so many things together. So now a few areas of programming education research. There's as I already mentioned, that already in the early years there was research on novice and expert knowledge differences. One of the main differences there is that experts have lots of schemas that they can apply, and they have schemas on different levels of abstraction, and they can fluently move between different abstraction levels when considering programs. There's work about students' mental models, so that what they have mental image about what happens. While this might not be totally correct, but it works in some conditions, and so we are calling these viable mental models, but they might not work totally. So when the ideal thing is the conceptual model, the mental model is students' understanding. And very often students have some misconceptions about how things work, so systematic wrong understandings. Then there's a lot of work on developing the programming skills, because what you need to be to learn to become a good programmer is you need to build a repertoire of strategies. You need, for example, not just the programming language constructs, but you need to understand how you select the appropriate algorithms and data structures for certain for specific goal, how you test and debug in different ways your programs, what kind of design methods there are, and what kind of design criteria there are. So there are lots of complex things that you need to learn, and of course not all of these are learned in the first programming course, but over many courses. One of the observations is that there are students who could be characterized as stoppers, so that when they are programming and they face some problem, they actually stop, so that they just kind of give up. I don't know what to do. Then there are movers who then have patience. Okay, let's try something else. So I will push through this. So they have a motivation. Okay, we'll try until I get it done. And then there are what can be called tinkerers. So students who try something but without any kind of good strategy, so that they make even arbitrary changes to the program to just test that might this work if I make this small change. Then there has been lots of work on trying to understand that why there are so big differences in that, so that some students learn programming well and some have serious problems. So various background factors have been analyzed, but as a summary, there is no such a combination of factors has been found which would clearly predict that how students learn their first programming language. However, there are a couple of factors which are relevant here. Student self-efficacy and how and their emotions. When of course when you feel frustrated when programming and there's a problem that you cannot solve, and these emotions can have a positive or negative effect on your self-efficacy. Then there is fixed or growth mindset issues that some students think about, that okay, I cannot learn this. I cannot learn this, or that some students think about that. Okay, yes, I'm struggling, but I will be able to develop my skills. Then there's how we can get students engaged with learning programming or computing in general, and what kind of self-regulation skills they have. All these things are relevant in computer education. Just the example of few pedagogical methods which consistently have been shown to have good learning outcomes is pair programming, where students work in pairs, switching their roles, so that one is coding and another is observing and commenting, and then they switch roles regularly. Media computation means that the programs are focusing on media, like manipulating images or sound, and that makes kind of motivating examples, seeing where the impact of the program in a concrete visual way, instead of just focusing on numbers. Then peer code reviews, so that students together with the teaching assistant, they are reviewing code, comparing various solutions, and that way learn about others and what are pros and cons of different constructions. Then let's go on to an area called tools research. So there's a lot of work here. The basic idea there is building software or hardware applications which support learning or teaching computing. And many of these tools, they are quite elaborated, and there's a substantial effort in implementing them. It's a very important area, and especially in interactive programming. So this gives an image of that. Then there was an extensive review a few years back, only 15 years of papers, finding 255 papers about tools in this, over 1,600 papers on interactive programming only. So not in whole computer education, but really about interactive programming. There are many categories of tools. There are clear applications that you can download, like BlueJ is a very famous application for learning Java programming, which you can download to your computer and run there. Then there are web services that you can run with your browser. For example, Peerwise is a tool where students can generate multiple choice questions for each other and then grade each other's multiple choice questions and how well they are constructed. And this is supporting a pedagogical method where students are contributing to learning by making they're making tasks for each other. There are software frameworks with which you can build applications. I'm showing an example of Parsons problems shortly. Then there are educational programming languages, for example, Logo or Scratch, and then physical tools like robots. There are many different categories of tools, like educational programming environments, specifically designed for supporting learning programming. Then, because professional programming tools are very elaborated, then there are simplified versions of those ones, which have been created using various libraries. There are various visualization tools for programs and algorithms. There's automatic assessment tools or giving automatic feedback, intelligent tutor systems, and so on. So I'll show now some concrete examples from my own team. So here's our programming learning environment. I'm actually the learning management system. Here, a very simple program that you take running times from a text file and just categorize them how short time there was in three categories. Okay, this is a very small, simple program, and we can automatically test that. I'm not showing actually how I submit it, but I just submit one file, and then I get test results. There are several tests which have been carried out when various things. I'm passing some of those, but then there are some problems here. Valid files, so the file format is okay, but something I have kind of miscalculated, that it's showing that my program outputted these numbers 4 and 6 here, whereas the actual expected output would be 5 and 5, indicating the differences. And that way we can provide with the test information for students about their program, how it works. Okay, so this is what we are frequently using on our courses, these kind of things. Two students get this test feedback for them immediately after they have submitted. And then other errors here. Then I'm showing example about data structures algorithms. So here's a visualization tool where students can manipulate what is called a minimum heap. So it's a binary search tree where the condition is that the father node needs to have a smaller number than the children node. And student here's the pseudocode there what the student sees, and now the idea here is the student is giving here a number of input values and then starts filling on the tree. And when the minimum heap conditions violated, student switches the values, then inserts new values. And then I'm not doing to the own, but student can then ask grading for that. Okay, and got some of the steps were correct, but of course I wasn't doing it till the end. So we can give the students this number, but how well they did, and then they can reset them. And then they get always a new set of numbers to be inserted, and they can train this conceptually how this minimum heap algorithm works. And then they can look at the model solution, how it works step by step. They can do this. But after model solution, they cannot resubmit the same solution. They need to have a new set of numbers. Then we have a program visualization tool here. So there's a simple Python code, and I can step through and there's an explanation what happens in each phase. So what happens? Okay, so there's a comparison. The result is true, and then proceed. Okay, we print something. And student can so browse visually that how program execution proceeds, and also going backwards there, and that in that way understand how the program executes, because normally when you're executing program you don't see how what happens under the hood. Then there are Parsons problems, where idea here is the construct the program which looks at whether the temperature is under 15 degrees, over between 15 and 25, or over 15, and should then produce whether it's cold, hot, or moderate. Okay, I make here if it's below 15, then it's cold. Should Python here. So then we at else if it's below 25, it's moderate. And if it and then else I can drag and drop those ones, and else it should be hot. And then I get feedback, and here's a test. Okay, but something wrong here. Okay. But then it should be that if it's exactly or at most 15. So I put here, and also exactly just between not larger than 25, but could be 25, and then it's moderate. And then okay, I solved it. So here are just a sample of different tools that we have built to support our students. There are benefits for these tools is that this automatic assessment can provide immediate feedback for students 24 and 7. They scale for large groups, and the visualization tools make the hidden computations visible. But it's not just that you see the visualization. It's actually research has shown it has to be interactive. Student is engaged with that. And I also already mentioned that these programming environments can be simplified. But then there are challenges. Students may misuse the tools. For example, automatic assessment tools have the challenge that students use the tools as a testing device instead of learning to test their programs on their own. And that has been addressed with other tools, so that students need to submit their own test cases as well. And then a serious challenge is that building this interactive course material, which includes the software, is not trivial to develop and maintain, because the maintenance is the issue. That because this is software, then the technology stack below the tool, so operating systems, various library versions, and hardware, they may be changed. They are being updated, and these may cause disruptions in the software. Security issues need to be taken seriously. So actually developing learning resources with such tools, using them, it makes this learning resource project a software project. And then one challenge is that guaranteeing that some service is operating 24/7 is not easy. We actually cannot do that. We don't have resources for that. And so a weekend problem, server breaks down, students will have a service down. Okay, and I'm closing soon. Large language models have emerged in the last two years. You know ChatGPT, and it can solve a large share of first and second year course computing course tasks. So how should we revise our education assessment, and how should we, on the other hand, integrate these large language models tools into curriculum? And on the other hand, they provide great opportunities, because you can use large language models to generate new learning resources on the fly. We can use them to generate personalized assignments for students based on their interests. They can improve hints in program and understanding or error messages, and provide even a kind of AI tutor for students. Learning analytics can trace a lot of information about students working when we log their submissions, submission times, how they make progress, even keystroke level, and we get the very deep profile of students, how they are working, and we can use that to identify at-risk students or problem with behaviors, and anyway understanding the students' learning process, because we see what happens then when they are doing something. Okay. There's an example here that we have students' working is compared to previous courses, aggregated, that how students have solved their assignments and how well they actually made. So if we have students who previous years they submitted very close to the submission deadline, they are colored red. So the one student here, you are here, means that you are quite close, you are submitting too late, and you can use this information when you continue on the course in the next week, start working earlier, you can then have more space, more time cope, and prediction is better. In the same way that if you submit very quickly the new exercise, okay, then that's also a risk for you. So that if you really don't stop to think before you resubmit. And finally, some recent developments in the field. the field has been growing rapidly in the over the last 5-10 years. So the number of papers in conferences, number of submissions have been growing growing heavily. And at the same time, we have been in the field improving the review processes in conferences. Following the computer science tradition in computer education conferences, all submissions, almost every conference, submissions are done as full papers, not as abstracts. And so there's a full-scale review, and there is also meta-reviewing phase where a senior person is looking at the reviews, and the reviewers are discussing together to improve the review quality, and then these improved reviews are sent to the authors. There's growing interest in using theories and instruments from social sciences, and also growing trend of improving doctoral education. So that completes my my talk. So I'm happy to respond any questions.
Thank you, Lauri, for this presentation. There were some questions in the chat and in the Q&A. So maybe, Diolinda, if you are there, maybe you can ask your question orally to Lauri.
Hi, Lauri. Good morning. Thank you for your talk. When you were explaining the programming inside the educational research and said that there are problems in understanding the content of the problem, that example that you shown about Python, I think prior to the writing of the program and the coding of the idea, students have to acquire some rational mathematical thinking. Otherwise, it will be almost impossible to understand properly what they are doing. And nowadays, what I think we all see is trying to put mathematics aside from engineering and from programming. And that I think we are going to to say our students that mathematics is not needed, but then when they found the coding problem, they don't understand what they are seeing. That I think, so prior to coding, the student has to really understand what is the rational mathematics behind.
Yes, yeah. Yeah. So, is this more a comment or question?
Yeah. What you feel about that? What do you feel about the need to have a prior mathematical courses for them to not really understand? I mean, sometimes there are not the things that they are learning that are so important, but the way they think to think about those things to solve that really generates some chains of knowledge and chains of reasoning that they need then after to properly program.
Yes, this has been explored in literature. What are the mathematical skills, how they relate to the program performance, there are a little bit mixed results about whether the mathematics grades, for example, correlate with success in programming courses. But it's obvious that the mathematics trains abstract thinking, and programming is abstract, and that's why it's important that they train some skills, and mathematics also naturally has certain concepts which are close to programming, like variables, functions, expressions, and all of those are needed in programming, even though there are some differences. That, for example, in mathematics, variables and programming variables, they are somewhat distinct concepts, and they need to be explained to students. And also some notational differences traditionally in mathematics are not the same in programming languages, but anyway, I think mathematics is important, especially because of the thinking skills it develops.
Yeah, thank you.
Thank you, Deolinda. There was also a question of Johannes.
Yes. Hi.
Hi.
Thank you for your talk. I was wondering in terms of computing education and AI education, AI education being like teaching about AI. How do you see kind of the connection between these fields? Would you say AI education is a subfield? Like, what can we learn from also the long tradition of computing education? Because I feel we are just beginning, and it's different people who are researching it, especially also in the different domains, like, you know, in the medical education domain, they're doing a lot of things, and also in engineering education, it's starting. So I was just curious on getting your perspective on that.
Yeah, it's true that the AI education and machine learning hasn't been much addressed in these computer education research venues that I presented in my talk. So there has been papers, but only a small minority of those, and there is truly a paradigm shift going on that because machine learning methods and AI tools, they are bringing so much new opportunities for computing that the computing curricula needs some redefinitions, but that's really something which is still debated in the field. So we don't have any joint agreement that what should be done, but this the whole idea that how machine learning and AI can be used as tools to which are operating in different way, totally different logic compared to traditional programming. So students in computer, they need to learn both kind of paradigms that how to treat data. So I expect that there will be much work on that. Currently, the work where is very much focusing on using large language models, but that's kind of this what these models provide as opportunities as AI tools. And they can the research focused heavily on that what we can do as educators with these tools, even though there's of course a challenge that at the same time these tools can kind of ruin our traditional education because students can just use ChatGPT to generate essays and solve programming assignments and so on. So, and there is not yet good solutions, what I'm aware of.
Thank you.
Thank you.
And Felix, you raised your hand for a question?
Yeah, two quick questions. First, about publishing. I know that in CS, conferences are the thing, and journal publications are often considered to be less important. Is it the same in computing education?
I think it's a little bit more balanced, but clearly, just considering the volume of papers that is published, then the number of papers in conferences is much higher than in journals. But I think that high quality journal papers, they are also highly valued in the field. That if you get a paper in ACM transactions in computer education, that's a great contribution, and it's not easy to get in through that journal. Conferences have the advantage that you know that when it gets published, if it's accepted. In journals, of course, the time span is longer, but on the other hand, the key journals, they have made a lot of efforts to cut the publication time shorter, so that you would get the review results in 1 or 2 months, good reviews after that, and then carry out the revision so that you could get the paper by accepted, let's say, in half a year in total with all revisions. But then when it's published, then it depends finally, and that depends, of course, the journal publication rate. But on the other hand, currently, for example, ACM Transaction Computation publishes also just accepted, which are not a special issue yet, but they are already visible.
And the second thing, you focus a lot on, let's say, the applied coding stuff, computing. How does it link in with theoretical computer science stuff like algorithm design, optimization, complexity theory? Does it also fall in the field? Are there different narratives there?
It belongs to the field, definitely. There is work about theoretical computer science, learning that and learning algorithms, but their share of the total volume is not very large. So I cannot say any percentages here, but let's say that papers about programming education probably are tenfold more, well, perhaps 5 or 10-fold more in volume compared to papers in the theoretical computer science or algorithms. But for example, in the 6C Technical Symposium, there are frequently sessions which focus on theoretical computer science or algorithms teaching learning. But then there are many other themes also, which like these equity things, and then broadening participation, how to sell the field to school children as a future career, and many other fields as well. As I showed that this book, this book covers many areas, and so there's plenty of work, but definitely programming education, especially in introductory programming level, is very large.
Thank you, Lauri. Maybe I want to also ask you a question. I think it relates also to what Deolinda has been saying. Like, of course, we have related in neighboring engineering education fields like math education and physics education. We also tackle particular misconceptions, and then we also try to provide a kind of feedback or prompting or whatever strategy to reduce the misconceptions. And I noticed in the programming example you showed that there was a lot of wrong correct feedback, and I was wondering if you have also been trying to detect what kind of misconceptions the students have, because of course right or wrong is really easy, but then understanding what's underlying, that's a lot more difficult, at least in physics. So what's your experience there?
Yes, there's this misconceptions, and research has been active, and there are dozens of different misconceptions in programming that have been identified, as well as in algorithms research where it has been explored. There have been work in developing a number of concept inventories for computing education, covering various areas, and that's an increasing trend of building such instruments. So though we need reliable measuring tools to identify the students' challenges.
Thanks a lot, Lauri, for sharing. I see it's already 1 o'clock. So first I want to take the opportunity to thank you for sharing your chapter and your insights into the computer engineering education field. And then I want to thank all the participants for being here, and also be aware that there are some more upcoming SEFI at Work sessions, both in this series, but also from other series like the Engineering Education Ethics Handbook. So don't hesitate to connect to SEFI in the future as well.